So if you have that, you can take a look at Fugaku data. Why do I have two of them? Is that an old one? Might be an old one. Oh no, that's okay. There's a Fugaku data. There are lines. It's a little bit small right now. Sorry. How do I make it bigger? 1 second. Yeah. No. Okay. Okay. Now it's bigger. And then you can fill out your memory bandwidth. Your total flops. So that's the amount of floating point operations you're doing. And then the runtime. Because the amount of floating point operations basically dictates your spot in the roofline on the arithmetic intensity. So let's figure out the runtime first. So average runtime is here. Ew. Where did my mouse go? Mouse? There's my mouse. And floating point operations, how many floating points operations are we doing? Remind, we have the B, and then we basically scale, so there's one multiplication and then there's one addition. So 2 floating point operations per element. We have 44 million elements. So yeah, I think I have the number somewhere in the slide. Maybe, maybe not. Did I put it somewhere? Oh, I didn't. Okay. And we just calculate it quickly. Echo. Let's wait. Grab array stream dot f. There's our number. I'm doing a little bit of bash magic now to do the calculation. I'm lazy to times 2. Oops, times 2. And that one actually says total gigaflops. So we want to modify that. That is kilo, mega, and then giga. So it would be 0.0, I believe. Wait, let's double check that. Divided by 1024. Let's take 1,000. Divided by 1,000. Divided by 1,000. So kilo, mega, giga. And of course that doesn't work because, because bash doesn't do floating point operations, so we do, so yeah. Okay, so 0.08 gigaflops. There's another one, memory. Here is in gigabytes a second, and my stream operates in megabytes, so we will have to adjust this as well. Megabytes, gigabytes, you're just moving the comma by 3 things. So we have 18 gigabytes a second, 0.08 gigaflops, flop, not flops, sorry. Gigaflop, and the runtime. Okay, so that's our initial result. And then if you have GNU-plot installed, you can ignore that if you don't have a GNU-plot installed, just skip that step. I hope I have it installed. Let's see. There's a roofline file, and then you open show. No, show image. Show image to. Right. Peak performance. You have to go into the roofline file first. Sorry, GNU-plot. And there are a few items you have to fill out. One is the gigaflop for A64FX. and the memory bandwidth. So I already said memory bandwidth is a terabyte a second, and gigaflop A64FX. Let's find the exact number. A64FX, FP64, peak, Fujitsu. There's the processor specification somewhere. I think they had documents, data sheet, infographic. I guess it's in the data sheet. Peak flops, double precision. Let's assume 2.2. Oops. Hello. It's 3.3 tera. So we have a floating point performance of, in gigaflops, 3379.2 and a memory bandwidth of 1024. Those are your specifications for Fugaku, or for A64FX chip. Okay. GNU plot, and wait. It's not LS-RU. I guess, is it that one? February 1st, yeah. So there's a roofline file, slightly different called, just do a store. Okay. So now you see roofline performance of your triad benchmark, and you see that you're far away from the roofline. So that's essentially your arithmetic intensity, also already said, your gigaflop performance, the roofline to like 3000 gigaflop, memory bandwidth here, and your triad is down here. And you see that there's a big gap between the maximum bandwidth and your achieved result, which is not good. So you want to actually close that gap, because stream should be very close to the peak of the roofline. So, oops, we make that smaller. So how can we close that gap is now the question. Theoretically, you have 1024 and you achieved like 18, 14, something like that. So it's an order of like 65x away from peak. And we have 48 cores, and that's like a very close number to like 65, right? Almost, a little bit away. So the question is your stream actually running in parallel? So are there parallelization issues with your stream? And we can, like one thing to check what's going on is like running the compilation, and what you see is like you're having GCC command, okay, yada yada, Fortran. And if you remember Bernd's tutorial, then you remember that using OpenMP, you have to tell the compiler to actually use OpenMP. So you go into the makefile, you check what's going on, and you see in the makefile there's a CC for your compiler, compiler flags 02, Fortran compiler FF for it's gfortran, and then FF flags. And you see there's no OpenMP related things. So what you want to do is you want to add OpenMP flags to your compiler. MP. So you add this to the C flags and to the Fortran flags. and then you compile again. So now in the make output, you see you have the F OpenMP, which is good, and then you execute again. For good measure, you can probably do this OpenMP num threads 48 to specifically tell OpenMP runtime to use all the threads. It may not make a difference, but if you want to do like a sub benchmark on like one of the CMGs or something, then you have to like play with those. But I can, let's just specify them. OMP num threads equals 48 and then stream. And we run that. And this seems to have fixed our OpenMP issue. The nice thing is now we are actually getting the information that we are using 48 threads. Before there was nothing, and now we are in a parallel mode and we see the benchmark, hey, 48 threads, nice. And the performance improved. We are at like 70,000 megabytes a second. We can play with those flags if you like to double check. Hey, let's do 16. And you see num threads changes to 16. And then you get also a number. Okay, so go back to 48. We have the 70,000, which is like 68 gigabytes a second, roughly. So we use that result, and we are going back to our plot. Where is it? Roofline? No, Fugaku data, sorry. F data. I should make that slightly bigger. So here we put this number and we move the comma. Next, we use the same flops because we have not changed the flops. It's still the same amount of like floating point operations you have to do. And the timing, we adjust the timing. So if we plot this, we see that our second example slightly improved on the roofline. So the first was down here, the second is up here with the cross. Very nice. But we are still away from peak. So what could be a reason for being still far away from peak with such a trivial benchmark? What could be the reason why we are still far from peak? Even so, that's a very trivial benchmark. We already took care of OpenMP. We increased the amount of vectors we want to run through, so we are in the HBM. Why are we not getting like the maximum performance out of our HBM? Maybe not enough arrays on the system. No, in this case, we already increased by a lot. So that's not the reason. The one next to her? What do you think? If we would affect the flops number, then we would essentially go left and right on the x-axis because we would adjust the arithmetic intensity. So that's, you would essentially change the benchmark. You don't want to do that. What do you think? You don't know? Okay. Okay. Basically, I can tell you that the system was designed by Fujitsu, and Fujitsu recommends their own compiler. That's the Fortran compiler and the C compiler and the C++ compiler. So they have their own version, and GCC may not be ideal in this scenario. So you switch to Fortran, to Fujitsu's compilers. So we go into the makefile. Bernd yesterday told you what the compilers are. So it's an FCC and it's FRT for Fortran. So those are the two compilers by Fujitsu. Bernd probably told you PX in the end. Those are for the login nodes. Since we have an interactive shell, we don't have to deal with the login node compiler. We directly deal with the compute node compiler. So they don't have this PX suffix. So we changed that, those two lines. We go out, we recompile. It should understand both. Yeah, I think so. Yeah, it understands both. Yeah, K OpenMP is the better flag. If you follow the guidelines of Fujitsu, but in practical terms, it understands F OpenMP. It's a little bit compatible for people who don't want to change their make files all the time. So Fujitsu compiler now recreated your stream benchmark. You run again with 48 threads, and what you see is, yay, it improved a little bit. That roughly matches what I have on the next slide. So we can put that into our fdata file. There, we move the 0. Oops. We copy that one, and we put the number for the timing down. And we see it's slightly improved. So the next dot, slightly higher. Nice, but still far away from peak. You're still at like 1/10 of the peak of the chip. Yes, sure. So it's FC for the CC, then -02 minus K OpenMP, and then FF has an FRT for Fortran short, essentially. And the same flags for OpenMP. You're good? So as I said, you're getting slightly over 90 gigabytes a second, and your boss is still not really happy because he says like, hey, specification, a terabyte a second. You're just getting 1/2 of one HBM stack, and there are like 4 HBM stacks, so what's going on? Not nice. You have to fix that. Right. So what could be the reason? Now it becomes a little bit more of a technical thing, which most of you probably don't really are familiar with, but if you, how should I say that? So you have 4 HBM stacks, so 4 memory modules, and what you want to do to exercise all of them is essentially distribute the data across all of them. What happens here is you're probably just using one of the HBM stacks, and that's why you're getting just like slightly less than the performance of one stack. That can have multiple reasons. Either is your benchmark is faulty because it does not put the data in the right place, or your compiler is faulty, it doesn't do the right job, or the OS is faulty, it doesn't put the data in the right place. There can be various reasons, or your data chunk is not big enough, and then it puts all into one HBM stack. So it can be a magnitude of different factors why you're only using one HBM stack instead of 4. And you may have heard from Bernd, not sure about this, but you may have heard something about first touch policies. Have you introduced? No, you haven't introduced. So what first touch is in the OpenMP land, if a core creates a memory region, like a thread, so sorry, an OpenMP thread creates a memory region, the memory will be allocated closest to the core. So if you have 48 cores and the first core thread allocates all of the vectors, then all of the vectors are on the memory closest to this thread. So that's what they call first touch. You can play with that if you allocate the memory and then like the first time you write into the memory region on all the threads, then the memory will be distributed closest, so the like pages and things moving around, etc., etc. Not too important, but essentially what you would do is every core gets the memory chunk allocated closest to the thread running on that core. And so we want to enforce that the first touch is essentially distributing the memory across all 4 HBM stacks. And it's not that easy to do with the compiler, but it can be easily done in the benchmark code. So we go back into the benchmark code. That's one of the issues. This old Fortran code, they didn't have those problems because they didn't have multiple HBM stacks. There was like one memory, so it was easy. There was no issues with first touch, so the code didn't have that. So we want to fix that. I'll go back for now. Stream.f. And we want to look for initialization of the vectors. So we see here, okay, our array size is fine, program, that's the start of the program. We have a bunch of like variable definitions, all doesn't matter, blah. A few like OpenMP information, doesn't really matter much either. There are still, here are our vectors, so of a certain dimension, not too interesting. Some data things, elements, they're essentially like global variables or like data chunks, doesn't matter too much either. Here you have some print statements, not too relevant. And here you have the information that the master thread is telling how many threads are the benchmark is running with. Some more information here. What we see here is a do loop, like a for loop, which sets A, B, and C. And that is essentially your first touch. That's the first time you're touching those arrays. So you want to modify this. And what's essentially what you have to do is an OpenMP parallel for, so that this for loop is parallelized. I believe there needs to be an end OMP. And parallel for after the continue. Continue is essentially the end of the for loop in old Fortran speak. Don't worry too much about it. So there's a do loop across the different vectors and then an end for. You put that in. So it's like exclamation mark, dollar sign, OMP, space, parallel, space, for, and then the same with an end in between, which comes after the OpenMP. And then you have OMP and parallel for. We compile this. Oh, clause is inaccurate. What did I do? Maybe it's the wrong statement. Let's see. Wait. Maybe. Where did I have that stuff? Extra character font after the syntax 80 76. What is 76? 76 is that. Was that not OMP parallel for? 1 second. Let's see. OMP parallel for loop. OMP parallel do. Okay. It's do in Fortran land. It's for in C, C++ land. So let's change that. Sorry. It's do. Makes sense because it's a do loop, not a for loop. My bad. Do. Oops. I'll do. Okay. I should have just checked further down because there are also like parallel do loops. So I should have checked that. Okay. So OMP parallel do, OMP parallel and OMP and parallel do. Make. And it compiles. Yay. And then execute. And now we get stars. To the stars and beyond. So your boss is not happy either. What's going on now? Has like print statements with specific sizes. So your, let's see. Where's the print happening? Try it. No, okay. Validation, some subroutine check, check, answer. Where is it? Huh. Yeah. So there's a line in 162, it's a format specifier. And what essentially happens is your predefined format specifier does not have enough space to visualize the floating point number it's trying to visualize. So I think that should be, if you do it 12, I believe that should work. Let's see if the 12 works. Yeah, 12 works. So what you have to do, oops, sorry, I didn't want to recompile. I wanted to go into the file. You go into the file, you search for a line which starts with 9050 format, and then A 4 times floating point number, and there used to be a 0. So that is essentially like, hey, I give you 10 elements of space, I believe, and then four numbers after the dot, and you just have to increase that to 12. It's in line 160 and 4. And that is essentially just telling the Fortran 77 so that you can fit a number bigger than 10 like elements there. So you have the 4 after the dot, and because we ran over, we had more than 100 or like 70, no, sorry, more than 10,000 megabytes, we need one more space essentially to get there, to visualize this number. So the triad bandwidth we achieved is now quite substantially higher. We visualize that, pretty close to peak. Not there yet. We have about, what is it? 631 gigabytes a second. So that's about 63% of peak. Quite a substantial jump from like 90 where we came from, or initially like 10-ish. So we are getting there. Quite nice. By the way, when are we like supposed to have the break? Regina? Someone? When is the break supposed to be? 12:20? 20, okay. So I have a few more. So theoretically, if you talk to other people, they will tell you that on a stream benchmark, you should usually get about 80-ish, 90-ish% of peak. Since we are getting like 60 something, we are still a little bit far away. The question is now, is the chip problematic, or are we doing something wrong? Can we improve on the flags? Can we improve on the OS, etc., etc.? And what you would do in this, yes? Okay. 12:30, you mean? Okay, yeah, thank you. Okay. So what you would do in this scenario is you would look into like documentation by Fujitsu, into like hardware manuals, talk to your colleagues, see how you can improve the performance. One thing, when you read the manuals, like here I say like check the compiler flags, improve the array length, the thread count you have to analyze. First touch we already fixed, the printing we fixed. Compiler flags seem to be okay. And if you read the runtime manual for like memory allocation and stuff, you see that Fujitsu recommends a certain paging policy, which essentially defines how memory pages are allocated and moved between the chips and stuff like that. So we can try that out to improve our performance. So that would be an external factor because it defines how the operating system or it's like libraries of Fujitsu are handling the memory allocation. So that has nothing to do with your benchmark itself. It has nothing to do really with the compiler. It is more an OS feature or a library feature of your specific chip. To copy this, paging. I want to change that. Okay. Copy up this. And there's something like pre-page command instead of on-demand. So we are changing the paging policy as recommended by Fujitsu in some of their manuals. And we see if we can improve. And we actually didn't get a substantial jump. Okay, something is weird. So we have our paging policy. Change that. Okay, so it was not the paging policy. So we have to look a little bit further. Back down to like 90 gigabytes a second. And your boss is getting slowly making fun of you. So it might have broken your first touch because you remember when we didn't do the first touch, we had like 90. Then we added the first touch. It improved a lot. And now we are doing the paging policy and we are back down to 90, which is roughly the same. So it might have broken the first touch. So yeah, back to square one. So what can we do now? We can play with the compiler flags. So Fujitsu, in their infinite wisdom, added some information into like deep down performance tuning manuals of, hey, if you have memory bound stuff, you should play with those like prefetching flags and zfill flags and stuff like that. And the prefetcher is essentially, there are two mechanisms how the compiler, how the CPU prefetches data from the memory. One is the hardware prefetcher, where the system basically just decides, hey, you access this memory, and then this memory, and then this memory, and then this memory. So it's very likely that you're accessing this memory, this memory, this memory, this memory consecutively. So the compiler, the CPU just like, oh yeah, just give me those pages from the memory, like, hey, bring them in. The user will use them in a bit, it's fine. So that's hardware prefetching. But then Fujitsu also added prefetching. And so the compiler can analyze the code, and the compiler can determine that certain array accesses will be contiguous. And if it's a long array, then it's better to instruct the CPU by the source code to prefetch those memory chunks. So that's what essentially those k-prefetch instructions are doing. So we are going to software prefetching instead of hardware prefetching. And then you're telling like how much data you want to prefetch. And then zfill is another thing, essentially for like write back, if you're like writing information back to the main memory. So we want to play with those things. And where we do that is in the make file. And sorry. I have to copy that. Copy text. Okay, so, but you have to give it some like numbers. Just select random numbers for now. Something, I believe the manual tells you can select something in the order of like 1 to 100 or so. We just select something and we'll see what happens. And we need the same here. Oops, that's not what I wanted to copy and paste. Paste. 14. 12. We recompile and execute with the paging policy. And hasn't changed too much. Got a little bit better. On demand, sorry. Have to change the paging policy to on demand. I'm sorry. Because that was the recommendation by Fujitsu for this particular test. So we are doing that. On-demand paging. And we are back to 760 gigabytes a second. Yay! So we are getting closer to peak. We are now at 76% roughly. roofline, and we see our triad performance very close to the roofline. There's still a gap of about like 25%. The question is, can we close that gap? So you're slowly getting there, your boss is slowly getting happy, but other people have reported like 900 gigabytes a second, so something is still going on. Fujitsu said like the chip, yes, the theoretical peak is like a terabyte a second, but like in practice you typically get like 900 at most. So the question is, how do we close the gap between the 700 and what is it? 760 to like the 900. And basically, right now, what we have done is we basically guessed those benchmarking parameters. So the prefetch line width and the zfill instructions. And we would like to know what is the ideal number, not what is like our random number. Random number seems okay, but it's not ideal. So what we are now doing is we are doing a parameter sweep. Those benchmarks run relatively quickly, which is fine. Exactly. So basically means we can sweep over those two parameters quite easily, test different configurations, and then see which one gives us the highest performance. So we're just playing with those numbers. And for this purpose, we actually have to modify the makefile a little bit. So as you see on the next slide, we have those parameters for the that was the, okay, I'll just stay here and modify it here. Is pref for the prefetch and zfill for the other one, so dollar brackets zfill. And then we can essentially from the outside world modify and give different parameters to the makefile so that the makefile creates different binaries for every run to automate the process essentially. Because you don't want to do that manual to sweep through all those configuration. That is, that's not fun. Okay. And in the same folder as the other binaries, the other files, there's a sweep.sh. You can look at this. And I already prepared essentially what to do. What's going on here is you're looping over two different loops for the prefill distance, prefetch distance, and the zfill size. You are setting those environment variables, and then you're calling the make, and then you're executing that benchmark with your paging policy and your OpenMP threads. Here, we want to have sane numbers, so sequence range from start, step size to end, so you are replacing the S and the E's. And we can do something like, in the slides, I recommended like 8 to 18. And the same on the prefetch, 8 to 18. Saving this, and then execute the sweep. So you're basically just doing bash sweep, and then your script will set those parameters, compile the benchmark, execute the benchmark, and then extract only the triad line to give you an information of what's the prefetch, what's the zfill, what's the performance. And we are seeing like, okay, with a 10-10 configuration, rather bad. With a 10-8 configuration, rather good. So we just wait a little bit to see what comes out of it, out of our performance sweep. There's a good one, 800. So that's a 12.8 configuration. There's another good one, 14.8. There's another good one, 16.8. 16.12. That seems to be the highest so far, 845 gigabytes a second. There's another one, 1810, which is relatively high. 1812 seems to be the winner so far. And yeah, that was it. And what we see is that the 1812 configuration, so very close to your initial configuration, is actually the winner in our today's exercise. So we add this to our Fugaku data. Actually, you have to add a new line. Try it. 6 line. Change that to that. Copy that. Copy the time. Where was it? I lost the line. There. 1812. Was it 1812? Yeah, 1812. Okay. Now we add this. So that's our last example. And can I make it big? Why does it not work? Okay, never mind. For whatever reason, it's not. I can try zoom. Accessibility. Doing some hackery. And 2x zoom. Ha. And you see, our last trial, trial 6, got about 85% of peak, which is decent. You can still play with other factors like increase your vector size and other things. So I think my personal best was like 920 or 30 at some point. But yeah, 85% of peak is a decent number and your boss will be happy. Good. So what did I report here? Yeah, seems to be better. If you look at the final speed up you gained, like from trial 0 to trial 5 or 6 in our case, since we reported an additional one, you have about 50x speed up in a couple of minutes if you know what you're doing and you know what you're searching for, and if you know Fortran 77. That's one. I know. But yeah, you can do. Bernd, did you show them yesterday the PyOMP stuff? No. Bernd, did you show them the PyOMP stuff? No. PyOMP? Ah, sad. Sorry. So if you don't want to do Fortran, you can do something like PyOMP. We can give you some instructions of how to do that. It's quite nice. So it's a JIT compilation of your OpenMP of your Python code with OpenMP, and then you can achieve similar results. Hopefully, I installed it, but I have not tried it myself. So take it with a grain of salt. It may not get to the full performance, and since it's PyOMP uses LLVM underneath, which does not come with all the Fujitsu goodies. You're probably looking at like 550 gigabytes a second for a stream benchmark at maximum. Maybe 600 gigabytes a second. That's typical if you're not using Fujitsu's libraries and Fujitsu's compiler, because they have like the prefetching and paging and various optimizations for Fugaku. But yeah, good result. Your boss will be happy. you achieved quite a remarkable thing of 50x speed up in a single day. Yay. And you can look at the slides if you were like if you couldn't follow in time, if you were just listening now, you can do the exercise yourself at home. If you run into issues, just ping us on Slack. We can give you some hints of what might go wrong, what might go right. Just remember, it's fun. Take it as a fun exercise. Benchmarking is an art, and you're learning over time. You will make mistakes in the beginning, and it takes a couple years until you become a profession. But most of it, you will need it, especially for writing papers, because in a paper you have to compare X to Y. Typically, you can't just like, hey, that's my solution, and here's my performance. You typically have to do, this is my solution and my performance, but there were other solutions with other performance, and I can show you that my solution is better because it's faster. So you always have to do some benchmarking exercises, and for that, I hope you keep the slides and the exercise in mind. And with that, I'm handing back to our lovely lady, and we are going to the break, I guess.
Yes, thank you. Please give him a round of applause. Thank you very much, Dr.